Enterprise AI systems rely on stability. Once an engineering team finds the optimal prompt to guide a model's behavior, that prompt gets locked into the codebase, acting as a static set of instructions for every future query. But foundation models evolve quickly. Eventually, organizations swap out the underlying model behind their API, usually chasing higher capabilities or lower inference costs. The default assumption is that an optimized prompt built for a weaker model will yield the same or even better results when fed into a stronger model. In reality, this migration consistently degrades performance. Applying a frozen prompt to a new target model triggers a semantic misalignment known as model drifting. We can see the mathematical proof of this drift in the HumanEval dataset. When GPT-5 is evaluated using a prompt explicitly optimized for itself, it reaches 99.39% accuracy. But apply that exact same prompt to a Llama 3.1 70B model, and accuracy plummets to 68.7%. Prompts are not universal instructions. They are highly specific artifacts, overfitted to its tokenization scheme, its human feedback criteria, and alignment corpus. You might assume this drift only happens when jumping between different corporate developers. What if the source and target models share the exact same architecture, just at a different parameter scale? Researchers tested this internal scaling theory on the XCodeEval dataset, mapping prompts across different sizes of Llama and Quen models. This matrix tracks the performance gap between identical model families. The darkest cells run diagonally, indicating that each distinct parameter scale requires a bespoke prompt to reach its maximum accuracy. Transferring from a 70 billion parameter Llama model to an 8 billion version, the larger model's prompt completely misfires on the smaller one. Model drift occurs across entirely different architectural families and between different parameter scales of the exact same system. Relying on a static library of frozen prompts guarantees degraded performance the moment your API updates. The standard solution to this problem is brute force. Whenever a model updates, engineers run heavy optimization algorithms from scratch for every specific task to find a new prompt. Running iterative optimization loops for hundreds of distinct production workflows generates massive compute costs, making it completely unscalable for active machine learning operations. PromptBridge offers a training-free alternative. It is a framework designed to translate existing prompts across different models without requiring per-task optimization. The architecture begins by establishing a baseline comparison between the two models. It feeds the models a tiny, computationally cheap stack of alignment tasks. These tasks pass into a calibration engine known as Model Adaptive Reflective Prompt Evolution, or MAP-RPE. MAP-RPE uses quantitative evaluation and reflective feedback loops. It tests responses, measures accuracy, and iteratively adjusts the instructions until it discovers the mathematical ground truth optimal prompt for the original source model. It then runs that exact same loop to find the distinct task-specific optimal prompt for the new target model. These calibration pairs define the precise structural adjustments required to align the target model with the source's original instructions. With these optimized pairs isolated, the system stops looking at individual words and starts analyzing the underlying logic connecting them. The paired prompts are fed into a mapping extractor. An internal model analyzes the pairs to identify systemic behavioral differences rather than just memorizing syntax changes. The extractor translates these observations into natural language rules, for example, noting the target model requires explicit code-only constraints. These rules are the core of the framework. They allow the system to execute zero-shot adaptation for entirely new, unseen tasks that haven't been optimized at all. We can see this applied back on the main pipeline. When an unseen task enters the adapter model, it applies the extracted rules directly to the old source prompt, instantly generating a fully compliant version for your target. Ultimately, PromptBridge removes the manual string manipulation from prompt engineering, turning it into an automated zero-shot compilation process. A systems engineer might question why structural rules extracted from one specific coding task would successfully translate to a completely different, unrelated workflow. The answer lies in semantic deltas. These are vectors that mathematically represent the shift required to move from an optimal source prompt to an optimal target prompt. If we plot this shift in a latent space, we get a specific vector pointing from the old model's optimal state to the new model's optimal state. When plotted for multiple unseen tasks, the resulting vectors all point in a highly similar, parallel direction. The empirical cosine similarity of these vectors confirms that the direction of prompt adjustment isn't random. It is a stable, consistent property of the relationship between the two models. Because these semantic trajectories are parallel, an adapter model can mathematically project any source prompt into the target model's optimal space, bypassing the need for per-task retraining entirely. In active deployment in enterprise environments, this mathematical projection solves massive logistical bottlenecks, particularly when migrating complex, multi-agent workflows. Consider a software engineering agent pipeline, originally calibrated on GPT-4o, that now needs to be migrated to the newer O3 model. We track the success rates using SWE-Bench verified. Attempting a direct transfer with frozen GPT-4o prompts yields a low resolved rate, but applying PromptBridge yields a 46% resolved rate, delivering massive performance gains without task-specific retraining. This dominance is consistent. On terminal bench tasks, the translated instructions again massively outperform direct prompt transfers. PromptBridge accesses the target model's actual performance ceiling, solving the migration trap, while bypassing the severe compute costs of reoptimization. This raises a final technical question. Why build a mapping extractor at all? Why not just use standard few-shot in context learning, showing the model the calibration pairs and asking it to deduce the pattern? When tested, few-shot prompt adaptation proved highly unstable. Language models tend to over-index on superficial details of the examples, like specific variables, rather than internalizing the structural rules connecting the models. By forcing the system to explicitly document the transformation rules, PromptBridge prevents that fixation. It yields reliable generalization across completely distinct domains. Static, manually curated prompt libraries cannot maintain performance across the current landscape of model fragmentation. Modern prompt engineering is moving away from manual string manipulation. By utilizing cross-model compilation frameworks, engineering teams ensure their AI systems remain optimized and resilient, regardless of which API sits underneath them.